How are the energies of everyone? So far, are we okay? Are we awake? Jet lag is fine? This guy is fine. I hope we are fine. Right now, we have heard a bit of very interesting and useful data. And what we're going to do now is to have a panel discussion, the first panel discussion of the day. Yes, please, you could put the slides up there. My name is Jose Pozo, and for the last 10 months, I have been the Chief Technology Officer of Optica. And I got a really, really cool job. I got the job of really getting to know fantastic people and fantastic companies, find ways for them to work together. In the last 10 months, I've been traveling the world, meeting with many of you, visiting many of your companies, understanding how we can actually bridge that gap. And the reason why I asked Peter if he would let me be part of this is because in one of those discussions, we talked to many semiconductor companies. And we asked them, what is the future? Could you go to the next slide, please? We asked them, what is the future of the photonics when it comes to semiconductor industry? In the last 10 months, we multiplied by 10 the amount of market data you have. And for those of you who have seen the latest optical transceivers market report from Yole, and for those of you, all of you have access to it now because we're Optica members, you have seen that I am really happy with some of the positive data that is there. However, I don't know if I have a clicker. Yes, I do. However, in another of the market reports, what we have seen is that we do miss in the supply chain of interactive photonics, we do miss the semiconductor industry, the semiconductor companies. Why are they not part of that? How can we bring them as part of that? So that's why I asked Peter, can we make a debate in which we bring some of the key companies that in the last year and 2 years, they have made huge efforts in reaching the semiconductor industry and to tell us about their experience and their challenges. For those of you who were at the Optica Co-Packaged and Pluggable Optics meeting in Silicon Valley, I think many of you were there, you all remember the presentation from Andy, from Arista, who told us, hey, if we stay in pluggable optics, we have the opportunity, he said, to bring new materials, to bring silicon photonics, to bring lithium niobate, to bring new organic compounds. We had that opportunity. To be honest, that opportunity is a nightmare because it's very difficult to bring these technologies to the semiconductor business. So in the next 45 minutes, we're going to have a discussion with some of the key people in the industry to understand how we can bring these new materials and new concepts into the semiconductor industry. So allow me to welcome to the stage David Piller from Dell Technologies, Michael Levy from Lightweight Logic, Peter Windsor from Nubis Communications, and Peter Bloom from Intel. An applause for them. I'm sorry, Robert Bloom from Intel, sorry. We're going to answer a few dilemmas that the industry is having nowadays. First of all, we're going to have what is the future of hybrid integration and how hybrid integration is going to be part of the semiconductor business. The second one that we're going to discuss is here. What new materials can we bring to semiconductors and how the semiconductor industry will accept those? We are also going to talk about opportunities for many of you on wafer level packaging. We will discuss a bit about your preferred future for the integration of electronics and photonics, and most important, how the silicon photonics community and the entire ecosystem can work together to accelerate the uptake of photonics technologies to semiconductors. And with this, I'm going to give the floor to one by one to all our speakers today to tell us about their vision and their preferred future. So let's start with one of the people who was participating the most on our co-packaged optics event in Silicon Valley, David Piller from Dell Technologies. Thank you very much for being with us. Tell us, what is your vision?
What is my vision? This drives things?
Yes.
Okay.
Your slides are coming up.
Oh, they are?
I hope so. The reason why we are here is because all of you have had different experiences interacting with the semiconductor industry. And here are your slides. Yes.
Okay, great. So, thank you, Jose. So I'm going to talk a little bit about success factors for silicon photonics. And, you know, first of all, I want to start out by saying, oh, now we're synced. Okay. Silicon photonics is a success. What's in front of me is not up there. Silicon photonics is a success. And for some of you, it's like, well, duh. I mean, we're having a whole panel on it. But in the world that I've inhabited for the last 5 years, I'm not working in an optics company anymore. People ask me about silicon photonics and how's it doing, because people have been coming up to them for the last 15 or 20 years saying that silicon photonics is going to rock their world. That's people at Dell doing servers and PCs and so forth, and all connections will ultimately be optical. Well, that hasn't happened over the last 20 years. So there are some other views. But what is silicon photonics? Essentially, it's a low-cost entry into the game of integrated optics. I mean, it used to be that to have a integrated optics business plan, you had to have fab as part of that plan. And the fabs, as people know, are expensive. So let's see if this works. Okay, so I just want to give an example of optical integration in the PON world, passive optical networks, otherwise known as fiber to the home. It's a world that I inhabited for a number of years, probably starting in the mid 90s. And everyone back then knew that you needed to have low-cost residential optical transceivers and optical splitters. And everybody knew there was this thing out there called integrated optics. At least that's what it was called back then. So to get these splitters, everybody knew how to make them. In fact, fused fiber optical couplers are extremely low cost on a per unit basis, and the entry cost is extremely low. I could actually start manufacturing these in my kitchen if I wanted to, but I don't. Optical transceivers, there's basically standard optics, lenses, mirrors, what's called bulk optics. Everybody knew how to make them. But when we looked at these things, we always were saying, oh, that's just way too expensive. We got to go to integrated optics, because how else are we going to meet these kind of cost requirements that the carriers are giving us? So, one example that was an integrated solution was a silica waveguide based on a planar light wave circuit. Now, I could have made a 1x32 optical splitter out of 31 fused fiber couplers. I'd only need 61 splices. I'd only need approximately 100 meters of fiber. So there was actually value in that it was something that was compact and tractable. There were also a number of companies that were looking at doing optical integration. And a company that I worked for, Photonics, actually was trying to develop these optical transmitters based on integrated optics. Not exactly silicon photonics back then, but a similar kind of concept, using planar technology, using the kind of technology that silicon fabs use. So who were the winners? Well, in one case, it was optical integration. They certainly won over the fused fiber coupler because it was compact. The startup costs were higher, but having 31 fused fiber couplers and putting them in a little box would be difficult. The optical triplexer was a winner, and one of the reasons that I think it was a winner is that for fiber to the home, you really only needed one transceiver per home. And integration doesn't necessarily work when you have a small number of functions. In other words, would there be integrated circuits today if people just needed one transistor per device? No, it's the advantage is when you have a lot of parallelism. So success factors for optical integration is to have a high degree of parallelism, and I call that N, like the 1x32 splitter. And the cost should be sublinear with N, and the value should be superlinear with N. And that kind of explains the experience in PON. But most importantly, the solution has to show a clear advantage over existing technologies for a number of reasons, both technical as well as primarily commercial, and looking at product development processes and so on. So those are just a few ideas I had.
Thank you very much, David. And now we have Peter Windsor from Nubis Communications. Actually, for those of you, Nubis Communications has been in stealth mode until about now. Right? And we are very curious of what you do. But Peter, the floor and the attention of everyone is nodding no. Are the slides up there for Peter Windsor? Yes, they are.
Yeah, so is the mic on? Yes. Yeah, okay. So Nubis Communication, I founded this company 2.5 years ago, and we're now 40 people, and we're still in stealth mode, so we're going to come out this coming week or the week after. That's the press release is already in the works. We are a VC-backed startup, and we are a team of about 40 really good engineers and business leaders. And we do have a website. You can see what's there. It's not much, but what I can tell you is we're building what I believe is the absolutely highest density optical transceiver on the planet, and at very low power. So, and that's going to be the optical interface for AI and machine learning predominantly, and Ethernet and mobile front haul as well. But AI and machine learning, that's where the real need is for high bandwidth I/O. If you want to see that in a very impressive video, I always advertise for that video from Tesla, Tesla's Dojo. If you go and Google it, there is the PI of that program has a YouTube video, 15 minutes out there, and they talk about everything from software to hardware, and their AI tile has 300 terabits per second of I/O bandwidth. Now that dwarfs everything that's happening in Ethernet these days. So that's where the action is, and that's where I/O is really needed. Okay, but that aside, we as a company are users of silicon photonics, but not just silicon photonics, also of analog by CMOS and also of digital CMOS. So, and that has been super interesting for me over the last 2.5 years to learn about those other fields. My background is in photonics, so I had to learn about analog by CMOS and digital CMOS. And with that, I think I have a pretty good overview of all the three areas and can speak to why silicon photonics is not at the level where CMOS and by CMOS is. So the abstract of this panel, gave me some smiles when I read it. The success of silicon photonics is based on the promise that it is a semiconductor technology, and hence it can be manufactured in volume by semiconductor fabs. So that is definitely a necessary condition, but by far it's not a sufficient condition. Not everything that's made out of silicon or semiconductors can be made in volume in semiconductor fabs. And the reason here is really that silicon photonics is still witchcraft. I mean, it's largely witchcraft. Analog by CMOS, you have to be an Einstein engineer to build these 100 gigabit, 200 gigabit amplifiers, and digital CMOS is just a software game. I mean, you still have to be pretty smart to build these microprocessors, but it's very, very much automated, and it's a nice process flow. So there is no witchcraft in digital CMOS. And that's really the short version of this big table, which I'm not going to go through, and I'm not going to expect you to read all of this. But I want to focus on a couple of things. So what I'm doing here is I compare silicon photonics, analog by CMOS, and digital CMOS with respect to various different aspects of it, from designing the chip, to modeling the chip, to making the chip, to testing the chip, to producing the chip. And in all of these cells, you can see how primitive silicon photonics is still, and what needs to be improved to get silicon photonics over there to become a true CMOS play. And it starts with the PDK libraries that are incomplete, and they are not optimized, and they are still, the foundries expect the users to characterize the building blocks. Come on, I mean, who would expect you to test the transistor performance if you tape out 5 nanometer TSMC? I mean, that's just ridiculous. And the incompleteness is also ridiculous. Maybe TSMC offers resistors and Samsung only capacitors, and if you want a resistor and a capacitor in the other technology, well, good luck, develop your own. That's where we are in silicon photonics. The same with the modeling software. Modeling software is at best fair in silicon photonics. It's super, super accurate in CMOS, and it's, I mean, in digital CMOS, you get back what you designed. If you don't get back what you designed, you didn't design it well, and the software would have told you had you done the simulation. The tape-out costs are low in silicon photonics, very low. but the turnaround time is super long. It takes 9 to 12 months to get chips back. To even MPWs are even longer, and that just is very frustrating. That gets this cycle of iteration, which is needed because there is no first time right design in silicon photonics. That cycle of iteration is just it kills progress then rather than enables it. Obviously the process is not as repeatable, the yield is not there, and you need to run these iterations to get to a product. Then from the support system, the IP vendor ecosystem exists in digital CMOS and to some extent in analog. It doesn't really exist in silicon photonics. You can't just go to an IP vendor and say, I want this block, I want that block, I put it together, it works. Packaging ecosystem doesn't really exist in silicon photonics. There are some efforts to get that going, but it's not nearly as advanced as in CMOS, digital CMOS. And the process volume readiness is just not there. Some of the foundries you tape out with in silicon photonics, once you ask them, okay, so can I scale this up to several thousand wafers a year? They say, not with me. But then you're stuck because you can't just transfer that, what you just developed with that foundry, go to the other foundry and say, okay, I'll do it with you in volume, because you start from scratch. You start at the very beginning, running your test chips, running your test structures, and the whole development process starts from scratch. So if you make the wrong choice in your foundry, you're screwed. That's it. For a startup, that's it. You have one chance, you have one shot. So that's the difference between silicon photonics and CMOS, and that's why we are by far not where we need to be in silicon photonics to make this a volume play. And there are many reasons, and we can discuss all these reasons in the panel discussions. Just want to set the stage here.
Thank you very much, Peter. Now we go to Michael Levy from Lightwave Logic. Thank you very much, Michael. Tell us, because you have really a lot of experience when it comes to interacting with semiconductor companies and bringing polymer to them, bringing organic polymer to make very fast modulation. The floor is yours.
That's true, yeah. I was going to ask you, Jose, have you got a pointed hat? Because I didn't know I was in the witchcraft business until this morning. But Lightwave Logic does electro-optic polymers. So we're essentially a chemistry company that does optics. And so we go, how do we do the next slide on this?
Green arrow.
Green one. There we go. And so we add electro-optic polymers to silicon photonics. And so it's a different technique. And this slide here talks about hybrid PIC. A PIC is a photonic integrated circuit. And so it's a bunch of photonic or photonic function devices on a semiconductor platform. But if you look at this, this table here on the left-hand side, what I've plotted are indium phosphide PICs, integrated photonic chips in indium phosphide, where you've got lasers and photodetectors and modulators and different types of passives. And so on the left-hand side in red is all indium phosphide. On the right-hand side is all silicon photonics. And you can see at the bottom there, you've got a number of different attributes or functions or devices you can get out of pure play platforms. So in indium phosphide, you can pretty much do everything except ASICs or large sort of transistor-based chips. You can do small scale, but you can't do large scale. And on the silicon side, you can pretty much do everything except laser, although Intel has merged indium phosphide to silicon and sort of half solved that problem. So pure play materials are not really getting us there. And what's happened in the industry over the last decade is people are looking to different materials to improve performance in various different ways. And so what I've plotted in the center there is a hybrid PIC. And that's a combination of indium phosphide and silicon. It could include polymers, it could include dielectrics, it could include other materials like thin film lithium niobate is being used today. And so there's a whole bunch of different materials are being added to either indium phosphide or silicon to improve the performance of that PIC, because the demands of the customer are such they better get the performance up. And so people are looking beyond the materials. And so when we look at integrated photonics, that's what we are seeing. And for us, electro-optic polymers generates really high-speed modulators. And because it's a liquid, you can spin it on and you can drop it onto a silicon photonics platform. So let's go to the next slide. So about us, from a very high view, we generate polymer material. and that's electro-optic polymer material. In fact, that's no different than if you're really thinking about the OLED business when you're looking at polymer LED displays. There are companies that develop that material, and they license and tech transfer that out to the factories, to the manufacturing plants, to the foundries. And so in some ways, you know, our business model on that top line there with the yellow arrows is similar to that. On the bottom line is, you know, what is unique about us? We make that stuff that's unique on the left-hand side, the material science. And so we get the performance there. But we have to work with CMOS and silicon foundries. We have a little fab in Denver, Colorado. It's 1,500 square feet. You're not going to get scaling and manufacturing volume out of a small fab. You've got to utilize the foundry system to do that. And once you have modulators working, or let's call it electro-optic polymer modulators on silicon photonics, then we've got to work with the transceiver companies. So we're not going to get into the foundry business. We're not going to get into the transceiver business. But essentially what we have is like a high-performance engine that actually allows the performance to increase for transceivers when they go into the network. And that's really where we are in the whole scale of things. And so this next slide, as an industry, the question remains, and we just heard from two folks here on silicon photonics to some degree, what we don't have. And this is my last slide. What we don't have is, from what we've experienced so far, we don't have a hybrid foundry for scaling. Maybe we do. But when we talk to silicon foundries, they're pretty fixed in their PDKs and their recipes because they're running CMOS. So when you're a photonics company and you have photonics dimensions and photonics components and designs, it doesn't automatically fit. And the first question is well, can the photonics folks change their recipes, change their design so it can fit the foundry PDKs? Sometimes you can and sometimes you can't, but it's actually difficult. And so the next bullet point, are our CMOS silicon foundries flexible enough, quote unquote, for novel modulator PIC platforms? It's an interesting question. We're seeing, you know, a bunch of foundries doing some good work, but is this the start, or is this something that we're going to engineer through, or we're going to have problems? Will existing foundries accept all the new technology platforms for modulators and PICs? Now, I'm sitting here at Lightwave Logic doing electro-optic polymers. There's thin-film lithium niobate, there's barium titanate, there's plasmonics, there's silicon, there's indium phosphide, and there's a couple of other materials. And so how do silicon foundries take all these new materials and integrate them into, let's call it quote-unquote CMOS platforms? It's not that easy. And then the last thing is you know, as an industry, we don't really know what hybrid actually means. But for me, it means it's not a pure play. You have a different material. It could be front end, and it could also be back end. And the reason I say back end is because if you look at the electronics industry, we've really gone to chip scale packaging. And the photonics industry is definitely heading that direction with chip scale PICs. We're getting rid of the gold box packaging, the old traditional package. And so chip on board, those types of directions are becoming important. And then the last point I have here is, you know, the industry really needs fast optical modulators. They want 3 dB bandwidths of greater than 100 gigahertz. Why? It's because the modulator platforms today are in the 20 to 40 gigahertz range, and it's getting us, you know, 100, 120 gigabaud in data rates using PAM4 and different types of encoding schemes. And what we actually have is we have electronics, expensive power-consuming electronics, that's actually helping the optics. And I think what we represent is we have fast optics, low power consumption, and so that may alleviate some of the power-consuming heavy DSP-type electronics. And so faster optics is certainly a direction we're going. But in order to do this, we've got to be able to work successfully with the foundries. And that's not easy. And I'll finish with one last point. And you said it, you have one chance. Well, maybe you have more than one chance, but foundries are expensive. So if you do mess up, it takes you 8 to 9 months to figure that out. And so we're actually working with more than one foundry because we can afford to do that. But it's still, you have to think about risk mitigation. It's not easy. And foundries screw up. I mean, they're human. They have supply chain issues. I mean, they have all sorts of problems. And so, yeah, it's a risky business. And there's a bunch of other issues that you went into, Peter, too. But this is not easy. And I'll leave it at that.
Thank you very much, Michael. And now we have Robert Bloom from Intel. Tell us, because Michael just said that we don't have a hybrid foundry. Tell us, what's your vision on this?
Well, before I start with the vision, let me first maybe talk a little bit how we got here. So at Intel, we started developing silicon photonics back in 2000. So we're now in the 23rd year of developing silicon photonics. Because we saw this need, or others saw this need, at Intel saw this need that, a lot of the electrical communication is going to move optical. We're running into bandwidth issues at the edge. But it took quite a while, really, for this problem really to materialize. And in fact, when we look at computer workloads, AI machine workloads that Peter talked about, this is really the prime use case. We'll see optics develop truly at scale, right? When every CPU, GPU will have an optical tile and massive amounts of data going in and out of the chip, not just in and out of the chip, but also going significant distances, right? Because you have these highly meshed architectures where you have multiple GPUs or CPUs clustered together, and you simply cannot do it electrically anymore, right? So this is a turning point, really, I think, for the industry that's just a few years away. I think the other interesting trend we saw was really the move from telecom optics to data center, datacom optics, which was driving, again, a massive amount. If you're putting this up, you have to fix my name here. I cannot look at Peter Windsor and Peter Bloom right next to each other.
It looks magic. Look over there. Yeah. Look over there.
There you go. Very nice. Thank you.
I don't know how it happened.
Thank you so much. And that happened really like 7-8 years ago. If you guys remember, sort of data centers moving to 40 gig optics, and the big hyperscale data centers simply couldn't get the pluggable transceivers because there was not enough supply. I remember, there's nobody from Google here, but I think Google had to qualify 7 suppliers to deploy 40 gig in their data centers, and that was just astonishing, right? And 6 years ago at OFC in San Diego, Urs Hölzle gave a keynote speech. I don't know if anyone was there, but he was talking about optics being a boutique industry and needing to really go to a mature industry that can make optics at scale, right? And that was, I really liked that talk because it spoke to what we're trying to do at Intel. So at Intel, we basically had, the IDM model where we were making those transceivers internally with our internal silicon photonics. But last year, we decided that we're going to open up our silicon photonics fab, which is a 300 millimeter fab on a 32 nanometer CMOS node, that we're going to open that up and start a foundry offering for that. And so I'm in the process to putting that together, and hopefully eventually get to a good PDK and easy design methodology. I agree, obviously, that we're not there yet as an industry. But I think there are quite strong foundry offerings out there already. And in fact, we acquired Tower Semiconductor last year, but the acquisition hasn't closed yet, in fact, right? And Tower, I know that Tower has a very strong silicon photonics foundry offering as well. So anyway, I just want to introduce myself and obviously look forward to more of a discussion now as part of the panel.
Thank you very much, Robert. And now the floor is open for questions, challenges, ideas. But here is the biggest concern of all. From what Michael said, there is no way around. If we don't bring these new materials to the semiconductor line, we really cannot keep up with the bandwidth demands. So we really need to bring them. At the same time, and Julia is going to tell us later, Jennifer is going to tell us later, there's going to be money for the CHIPS Act, and they want to invest in semiconductor fabs today. So the question is clear. How long do we have to bring these new materials that we need to semiconductors so we don't miss the train of bringing photonics into the CHIPS Act?
Well, I fundamentally disagree with Michael.
Wow! That's a good way to start.
That's a good start.
So, if we want silicon photonics to be successful, maybe we should look closer at the electrical integrated circuit. Nobody would claim that the one of the million transistors in my iPhone is a great transistor or is the highest end transistor, but they would agree that I have a lot of them. Actually, as we move from data center, going telecom data center, AI, ML clusters / high performance computing, there is actually a movement within that field that I don't know if everyone's aware of, and that's to go from narrow fast lanes, that is to have one very fast lane, to having many slow lanes. And there's a number of reasons you might want to do this. I won't go into the details. There's this guy down at Stanford, David Bloom's EE professor. He's been talking about this for 20 years. And I think the people who are starting to see the rubber hit the road in the AI, ML, HPC world are all telling me basically the same thing, which is good for silicon photonics, because now no longer do we have to worry about being at the very highest end, having the very best, most competitive, fastest modulator. It's just we have a good enough modulator, but we can make a hell of a lot of them in a very small space. So that's mine.
Micah, what do you think?
Well, I disagree. But it's also another strategy. If we think about what's happened over the last couple of decades, the modulator bandwidths haven't really changed that much. I said that earlier. And so we've actually improved the encoding schemes in order to deal with that. And so we have different encoding schemes. So yeah, we've been smart about it. It's like when you look at the freeway, we haven't really gone faster than 60 miles an hour, but if you go to LA, you got 6 lanes in each direction, right? So we just added lanes. In the photonics industry, we sort of stack cars on top of each other because we've encoded them. So each car now, if you can imagine cars stacked on top of each other going down the freeway at 60 miles an hour, that's sort of what we have done. Could we keep the speed the same, add more lanes, more encoding? Yeah, I don't disagree that's a strategy that could work. But certainly from what we see in terms of talking to customers and getting pulled, people want to go faster. Now, is there a limit? There could be a limit. But when you start looking at pluggable transceivers, I'm seeing roadmaps that show not only 800G, 1.6G, 3.2G are all on the roadmaps. The question is how do you do it? And how do you do it in an OSFP form factor, which is a pluggable form factor size of about 1 inch by 4 inches? And so it's a challenge. Now, perhaps David's right. You could do lots of slow channels in that form factor, maybe. I don't know. I haven't really thought about it.
You will need a lot to go to 3.2 tera and 20 gigahertz modulators.
It's a lot of data to put in and out of those things.
Yeah. Peter,
so there are 2 points for the fastness. So first of all, let's look at it from a historical point first. Why did we always go to faster and faster and faster and faster rates? The reason was that a single modulator, if you look from 10G to 40G around 2000, right? A single modulator supporting 40G was cheaper than 4 modulators supporting 10G. That's the reason why we went from 10G to 40G, okay? And that continued and continued. But once you're talking dense integration, the paradigm breaks down. If I build a highly integrated chip, the cost of building 1 modulator or 100 modulators, well, maybe not 100, but 10, 1 or 10 is the same cost. It's the same die, it's essentially the same cost. So that paradigm breaks down, which means from that perspective, I don't have to go that fast anymore if I go integrated arrays. That's one side of the coin. The other side, you need to think of it from a systems perspective, and there it might be totally different things that drive your decision. Because who needs to use those lanes? It's the Ethernet switch chips or the AI accelerators or what have you. So a 50 terabit Tomahawk 4 switch chip at 100 gig per lane has 500 I/O ports. That's 1,000 differential lanes. That's 2,000 bumps for the signal, not even counting ground. So that's just the signal. So you have 5,000 or whatever bumps on the underside of that chip that supply the I/O, and you haven't even put power into the chip yet. So you need thousands and thousands and thousands of these bumps. That's why you can't just say, okay, I run it at 50 gig or at 10 gig. Well, you need 100,000 bumps. That's just not feasible. So, and that's why the industry is going to 100G and then going to 200G, because the next generation chip, 100 terabit switch chip, now you have the choice. Do you build it with 1,000 ports of 100G, which then equals 10,000 or more bumps, or you stay with 500 bumps at 200G. And the reason you can't build so many bumps, that's why you need the high speeds. So these are the two contradicting things that are going on right now in the industry.
Hello, my name is Dmitry Starodub. I'm with D-Star Communications and I represent Art Photonics here in the US. What is really interesting about our industry is I was listening to the talks, and I think what we can compare photonics is not to semiconductor industry, but probably to gold mining or gamble industry. So we search for those unique solutions, and as soon as we find something useful and exciting, it just ramps up and becomes a treasure, and we got acquired, and then we become a part of a new adventure in a bigger company. And some of us probably went through this rodeo several times through our career. Now, right now we are heading down into a downturn, and it's just an exciting opportunity for an innovation. If you look at telecommunications, and we try to scale up optical comms to match the speeds of our iPhones, we suddenly see that we have to launch kilowatts of power through optical cables to match the data rates with the number of photons that we are currently using. So it becomes a challenge on scientific level where we have to combat nonlinear channel limits and invent new stuff. And I think right now it's that exciting and struggling time where we have to face new opportunities and invent new things and create new treasures, new gold. And I think silicon photonics is an exciting field that will bring us one of those opportunities. And I just want everybody to look forward to this downturn and create new things that will change the industry.
Dimitri, you know what? If I asked you that question 20 years ago, you have said the same thing. So honestly, I think so. Maybe I'm too negative now, but I really feel that this is the kind of thing that is happening, that we are repeating the same kind of statements, that it's CMOS compatible, that we need volume production. What can we do to accelerate? Because now we need to accelerate. The money is coming to the CHIPS Act, and if we are not suitable to be part of the semiconductor business, we are going to lose it. Robert.
Yeah, so I'm mic'd up here, so I don't want to get a big echo here. But the way I think about it is obviously from a foundry perspective, right? And we have a big fab, so we need significant volumes, right? And that the premise hasn't really changed. And so what we want to do is we do want a kind of a process, a standardized process that can serve many applications. We don't want to have super highly specialized changes, we call them dot processes, for each and every one application, right? So that's also why we're very careful about bringing in new material, or we won't bring something in until it's really mature and we can see that there's a real need. I would say that we do see obviously meaningful demand for standard data center transceivers type stuff, and then moving to what we call co-packaged, Ethernet switches. That's meaningful volume. We do see meaningful volume in some of the sensing applications like LiDAR, for automotive and eventually for consumer applications. We do see some potential in some of the biomedical stuff, consumer health sensing. These are all potential markets, right? There could be some demand for photonic computing, for AI accelerators or for quantum computing type stuff. So these are meaningful volumes, but also not huge volumes. If you add it all up and you look at it, okay, how many wafer starts per week do I have, right? And if it's not several thousands, I haven't filled my fab, right? And to get 5,000 wafer starts a week, that's a lot of demand at the wafer level, right? At the chip level. And so I think the biggest opportunity that we really see is for these AI machine learning workloads, right? Where we get to this, what we call optical I/O or optical compute interconnect, again, where we have optical tiles or chiplets interconnecting CPU, GPUs, right? Because again, once every data center CPU or GPU is connected optically, that is truly driving high volume. So I do think the opportunity is really here now, right? It is coming together. It's still a few years away, and even by the end of the decade, you know, I think if I look at all the silicon photonics fabs that are kind of out there, they're still going to be subscale. They're still going to be subscale, but it's happening, and that's why we're investing, because we see this on the horizon, and it's not just, you know, it's not past the horizon. It's really it's coming now.
David, we talk about many applications. We talk about LiDAR, biosensors. We talk about many different things. What is your take on this? How we bring everything together to go into the volume production that the Intels, the TSMCs, the Samsungs get excited about?
So I'll go back to the whole AI, ML / high performance computing application. So if you talk to people at these companies like Google and so forth, it actually turns out that you know, the data center has been kind of an overhead cost for them. I mean, it's just part of doing business. But AI, ML is directly connected to their advertising business. And that just kind of supercharges AI, ML compared to this data center stuff. Then on AI, ML, I just got to comment on some of the previous statements. It has a different architecture, different requirements. I mean, just Friday, I was talking to a high-performance computing company who typically has 10,000 endpoints basically in one room. And by endpoint, I mean the transmit to receive, you know, the nodes. You can call them GPUs, for example. And they want to connect them all together. And it's not, the requirements are very different from that of Ethernet. They can't deal with any latency. They can't use higher order modulation. You know, every time that you, from a power standpoint, every time you go to these higher speeds, I mean, if you look at your computer, have you ever seen a 100G chip? No, the chips run at like 6 gigahertz or something. You know, that's the fundamental speed that things want to be at. It takes power to add them up to be 100 gigabits per second, then separate them to be 6 gigabits per second. That is a waste of power, and again, that's going to drive this, I want to use the right words, slow and wide kind of application. And I think it will also make the acceptance of silicon photonics and take advantage of the advantages of silicon photonics.
And just to add, right, because you know, we see this overall. I had some discussion with someone about Moore's law, right, and what we're seeing is basically this advanced packaging, right? We don't have a single monolithic chip now. We have a package of chips, right, where they're all interconnected. For example, we have a co-packaging technology or interface called EMIB. We're driving towards a UCIe standard. So you can have really dissimilar chips made on different processes all packaged together. And there's a lot of innovation and development happening in the packaging area, because that's how you continue to scale Moore's law. You put multiple chips into the same package, and you go from a chip to multiple chips. And once we have that, and the UCI interface is exactly what David is saying, right? It's a much slower interface. It's wide and parallel, and that's what you need for this ecosystem really to mature. Right?
So I have a comment on that one. So I mean, of course, I'm very well aware of the slow and wide versus fast and not so wide approach or debate, but slow and wide has a big cost associated with that, and both in electronics and in optics, and we cannot ignore that. In electronics, that cost is very advanced packaging, because you need very fine pitches of the bumps that interconnect those dies in order to make so many parallel lanes. Those substrates are not cheap. So, and that actually prevents chiplets right now from being more widespread. It's the packaging technology. In the optics, it's the same thing. It's the lanes. It's like the electrical lanes, it's the optical lanes. Going super parallel in the optics means many fibers, which is hard to do because the fiber has a certain dimension, and that's given by the wavelength of light. Or you need to do massive WDM. And massive WDM is not a good data center technology because it consumes, it takes a lot of extra power to make very flat sources, to make WDM multiplexes and demultiplexes. They all consume power. They all have an insertion loss. A 3 dB insertion loss is 3 dB more, twice the laser power that you need. All of this needs to be taken into consideration, including the stabilization of these things. So it all has its price, and it's not so clear that wide and parallel is the right thing to do in my view.
Michael, what do we do to bring the industry together and we try to find a way to all work together? Because I do understand David's comment very well, very clear. So we want to adapt technologies to semiconductors because they want the semiconductor fabs to make it. But at the same time, we want to bring new materials so they adapt to ourselves. How can we find a way that we can all work together and be part of this chips and business?
Personally, I think, there's a number of big silicon fabs that have got silicon photonics programs, just like Robert was saying. And, a lot of these foundries are doing silicon photonics work. I would say that many of them, if not all of them, don't have the volume they're really looking for. And I think they're looking at this as an opportunistic business proposition, because if silicon photonics really takes off, they can run more wafers, because that's what foundries do. They just want to run lots of wafers through the fabs. So the question that we look at is, how do you integrate different photonic technologies with traditional electronic fabs? This is not easy. And this is why I sort of coined the term hybrids, because I think there's got to be some flexibility. Now the question is how much flexibility is reasonable? You go to the super big CMOS fabs and they're quite inflexible and they're very expensive. You go to the smaller fabs and they want the business, they're more flexible. PDKs are more, allowing for different photonic device structures and designs. And I think there's going to be a compromise here. But I don't know exactly where or when or how. But I do feel if there are foundries that really focus on taking in new materials, folding that into silicon platforms, it could be an indium phosphide platform too, it doesn't have to be just silicon. I think we'll see that, and I think that is sort of what I'm looking for. A level of flexibility on one hand, on the other hand, we've got to figure out how to get to some reasonable volume. And many people in our industry have said fiber optics isn't going to get us the volume we need to really excite these silicon foundries. So when you talk to silicon foundries, I guess I'm talking to one on the left here, they are looking more beyond fiber optics. They're looking to automotive, they're looking to sensing, they're looking at biomedical applications, because that drives some real volume. Like automotive LiDAR is supposed to drive tons of volume at some point. And so I think to answer your question, Jose, this is not easy. I think there has to be staged flexibility. Whether we call that a hybrid fab or hybrid foundry remains to be seen, but that flexibility has to come into play.